Our group consists of 6 members. First, Farah Shazliana, DF230112, Husna Abdul Razak, DF230072, Ali Patricia, CF230140, Fatin Shazwani, DF230071, Najwa Halim, DF230116, and Hanis Christina, DF230044.
Hi, my name is Fatin Shazwani binti Muhammad Samsul. To begin with our project background, the long-term stability of any structure depends heavily on the relationship between its foundation and the underlying geological strata. For this project, commissioned by JKR Kuala Lumpur, Geocrest Enterprise execute the dual-stage pipeline. We first simulated the structural frame in Esteem software to calculate localized column loads, and then conduct a comprehensive subsurface investigation to determine if a shallow foundation would be safe. The fundamental challenge at this site is the geological conflict between structural loads and weak coastal soil profile. Pulau Indah is dominated by highly compressible marine clays, thick silt, and loose sand layers. These materials have exceptionally low shear strength and high natural moisture. Building on such an unstable metric without precise mapping creates an extreme geotechnical risk, specifically ultimate foundation shear failure, massive differential settlement, and localized structure collapse. For the objective, first to determine the exact geotechnical engineer properties of the subsoil. Second, to provide essential empirical data for a safe cost-efficient design. Third, to retrieve high-quality disturbed and undisturbed sample for depth-bound mapping. And finally, to perform physical optimized investigation tailored directly to the coastal condition of project area. Lastly, our scope of study successfully bridged field testing, laboratory analysis, and analytical design. In the field, we complete deep drilling of borehole 1 to 60.45 meters, supported by standard penetration test, McIntosh probe testing, and continuous groundwater monitoring. In the laboratory, we execute particle size distribution at the back limits, chemical deterioration checks, and consolidated undrained triaxial shear tests. This rigorous data allow us to perform ultimate structural safety calculation using Terzaghi method with a strict factor of safety of 3, ensuring absolute compliance with it.
Referring to the soil profile shown below, the soil conditions vary significantly with the depth. From the ground surface down to 4.95 meters, the soil consists of very soft clay silt, which is presented by the yellow color. This layer has relatively low shear strength and high compressibility. Between 4.95 and 7.48 meters, the soil changes to soft clay, indicated by the beige color, suggesting a slight improvement in strength compared to the upper layer. The layer from 7.48 to 16.43 meters consists of a medium stiff clay silt, shown in a light green, indicating moderate strength and reduced compressibility. From 16.43 to 21.45 meters, the soil becomes a stiff clay represented by the light blue. Another stiff clay is also observed between 21.95 and 39.45 meters. At the depth of 21.45 to 22.95 meters, 39.5 to 46.95 meters, and 52.95 to 54.45 meters, the soil is classified as a very stiff clay, which is shown in gray. This layer possesses relatively high shear strength and lower settlement potential. Finally, hard clay layers are encountered between 44.95 and 52.95 meters, and again from 54.45 to 60.45 meters represented by the purple color. These are the strongest soil strata identified in the profile and are generally considered suitable barrier layers for the foundation system. Overall, the soil profile shows a progressive increase in the soil stiffness and strength with the depth transitioning from a very soft layer silt near the surface to the hard clay at the.
Moving on to the engineering properties of borehole 1, we look at the core geotechnical parameters that dictate the soil's mechanical behavior under structural loads. First, which is cohesion. The cohesion is very low in the top silt and clay deposits, which perfectly corresponds with our low SCPT and values of 0 to 7. However, as we go deeper, the cohesive strength rises robustly past 46.95 meter. This is due to severe geological consolidation and particle edging of the deep marine clay. Second, which is friction angle. For short-term or rapid loading conditions, we assume an underlying friction angle of 0 for the cohesive soil layers. However, the clay sand layer identified at 36.45 meter provides localized stability yielding a friction angle between 28 degree and 32 degree. Third, unit weight. The unit weight starts low at 14 to 16 kilonewton per meter cube within the porous silt surface. It then compacts to 18 to 19 kilonewton per meter cube in the stiff clays before peaking at the dense 20 to 21 kilonewton per meter cube inside our hard-bearing layer. Fourth, compressibility and settlement. The upper clay silt from 0 to 7.48 meter exhibits extreme compressibility, triggering immediate and long-term consolidation settlement risk. Conversely, the deeper, stiff to hard layers have already achieved high historical pre-consolidation, yielding excellent load-bearing structural safety. Finally, permeability and drainage. The overall cohesive matrix maintains exceptionally low permeability, preventing rapid pore water pressure dissipation. Yet, the clay sand layer at 36.45 meters serves as a critical, localized drainage pathway that can effectively expedite water dissipation rates during structural loading.
Assalamualaikum, I'm Nur of the project. This project proposes construction of a double-story houses at Pulau Indah. This project conducted to obtain geotechnical information on subsurface soil condition, conducted to obtain geotechnical information on subsurface soil condition, soil investigation data used to design and evaluate the foundation using esteem and houses layout and structure column loading and foundation requirement were determined from the structure design and foundation investigation were determined from the structure foundation design is safe and suitable for site condition. Study also help prevent settlement instability and structure condition. This study also help prevent settlement instability and structure. This project propose construction. This slide shows load for each column. The total load distributed across 19 discrete columns from column 1 to column 19. The process via STEAM software to resolve a depth, life, and environmental forces into localized vertical loads. Loads range from a minimum of 44.9 kilonewton at column C16 to a massive localized peak of 262.2 kilonewton at column C7.
The particle size distribution PSD by percentage is also an important engineering property of soils. PSD involves determining the proportion of sand, silt, and clay particles present in a soil sample based on their mass. For borehole 1, the soil profile consists entirely of fine-grained soils, ranging from a clay silt to the various types of clay soils from the ground surface down to the depth of 60.5 meter. Therefore, conducting PSD analysis is essential to determine the exact composition of each soil layer. By identifying the percentage of sand, silt, and clay, engineers can classify the soil layer and better understand their engineering behavior under the influence of water and applied loads. Soil with a higher clay content generally exhibit lower permeability, higher compressibility, and greater potential for volume changes, whereas soils with a higher silt content tend to have a different drainage characteristic and a mechanical behavior. Overall, PSD analysis is highly significant because it provides a more accurate representation of the subsurface conditions, enabling engineers to evaluate soil performance, and make informed decisions regarding a foundation design, settlement assessment, and overall.
In the design phase of Pulau Indah residential foundation, we encountered various structural loads transmitted through the building's column. To ensure a design that is both safe and practical for construction, we utilized a grouping strategy. Instead of designing a unique footing for every single column, we categorized them based on their specific load range. This approach simplifies the foundation design process and ensures that the system can safely support every column in a category by designing for the maximum load within the group. For this project, we have implemented a shallow pad foundation as our primary solution. This choice was driven by its economic benefits and the speed of constructions, providing the footings are sized correctly to distribute loads within safe soil limit. To ensure stability, all footings are placed at a consistent depth of 2 meters, and our design parameters are based on a soil unit weight of 16 kilonewton per meter cube. The mathematical standard for our calculation is Terzaki's equation. To ensure a high margin of safety, we applied a strict factor of safety of 3 to determine the allowable bearing capacity from our calculated ultimate bearing capacity to ensure the ground can safely support the structure. Moving to the verification phase, we compared the actual load demand against our engineered capacity for each column group to confirm safety. In Group 1, our demand of 68.7 kilonewton is well within the 274.56 kilonewton capacity. For Group 2, shows a demand of 107.6 kilonewton against a capacity of 322.898 kilonewton. Next, for Group 3, the demand is 217.3 kilonewton with a capacity of 374.99 kilonewton. And finally, Group 4, our highest load category has a demand of 262.2 kilonewton and a capacity of 431.21 kilonewton. As you can see, in every standardized grouping, our engineered allowable capacity drastically outpaces the highest possible column load. This confirms that our foundation design is not only safe but provides a significant buffer for structural stability.
Now, let's look at the serviceability check for our foundation design. The main goal here is to ensure that any compressibility in the supporting soil does not cause excessive structural settlement over the building's entire lifespan. We want to make sure the building remains completely stable and safe to use. To check this, we look at two critical safety thresholds. First, we have a strict limit of 25 mm, which you can see marked by the first red dashed line. Second, we have a heavy limit of 50 mm marked by the second red dashed line on the right. Now, let's see how our calculations plotted against these limits. For Group 1 and Group 2, the settlements were calculated at 10.2 mm and 14.8 mm. As you can see, both groups sit comfortably below our strict 25 mm limit. For Group 3 and 4, the settlements came out slightly higher at 27.8 mm and 31.2 mm. While they cross the 25 mm line, they still sit very safely and well below the heavier 50 mm limit. The verdict is a solid pass. Stable serviceability is fully confirmed. We have mathematically proven that critical structural fractures and building tilting are prevented, giving us absolute confidence in the structural integrity of this project. The calculated settlements for all footing groups are with the generally acceptable settlement range for residential structures. Therefore, the proposed pad footing foundation is considered satisfactory with respect to settlement performance and is expected to provide adequate serviceability throughout the design life of the building. The proposed shallow foundation is suitable for the calculated loading conditions. However, due to the existence of very soft clay and soft clay within the upper 7.48-meter soil profile, ground improvement or a deeper foundation systems should be considered if excessive settlement is anticipated. Next, let's talk about our geotechnical investigation and how we design the foundation for this double-story residential structure in Pulau Indah, Selangor. To design safe foundation, we first had to understand exactly what kind of soil we are dealing with on site. Our investigation showed that the subsurface is primarily cohesive clay silt and clay, but the most interesting part is how the strength of this soil changes with depth. At the surface down to 7.48 meters, we have a very weak layer of soil and a very soft clay. This layer is highly compressible and has low shear strength, which means it has a high risk of deformation under structural weight. However, as we go deeper, the soil gets much stronger. The middle layer transitions into medium stiff to stiff clay, and once we go deeper than 46.95 meters, we hit very stiff to hard clay. Here, the SPTN values climb above 30, indicating a highly competent robust bearing layer. This gradual transition from weak soil at the top to a very strong soil deeper down gives us a dependable basis for choosing a shallow foundation system, specifically a bed footing. To verify this, we utilized Terzaghis bearing capacity approach to run our design calculations. We wanted to make sure that the allowable bearing capacity of the soil can easily handle the structural loads from the building. And what did our calculation shows? Every single column group demonstrated an adequate safety margin. The permitted bearing capacity easily surpasses the applied structural loads. This mathematically confirms that our chosen bed-footing system is structurally sufficient and completely safe in terms of bearing capacity performance. But as we discussed earlier, we still need to manage the settlement risk of the topsoil clay layer, which brings us to our soil improvement strategy. Moving on to the soil improvement, even though our bearing capacity analysis shows that the design is safe, we do have a challenge in the upper soil profile, specifically the presence of a very soft and soft clay. These soils are highly compressible over time, as prolonged stress squeezes water out of the soil, a process called the dissipation of pore water pressure. It can lead to serious long-term settlement and consolidation issues. To mitigate this geotechnical risk, we have identified four ground improvement techniques that can be deployed during the construction phase if needed. First, soil replacement. We can excavate the weak surface soil and replace it with compacted granular fill to boost the near surface bearing capacity. Second, compaction methods. We can use techniques like dynamic or surface compaction to increase soil density and reduce the void ratio. We can apply a temporary load on the site to accelerate the consolidation settlements before the actual construction begins. And fourth, deep foundation alternative. If controlling settlement prove it to be highly critical, we can switch to a pile foundation system to transfer the structural loads directly down to the deeper, harder clay layers. Moving on to the special considerations, numerous critical geotechnical considerations must be evaluated in the foundation design owing to the coastal and alluvial characteristics on the site. First, subsurface water conditions. The site is impacted by a high groundwater table characteristic of coastal areas which influence effective stress and may diminish soil strength during construction. Second, risk of differential settlement. Fluctuation in soil stiffness ranging from a very soft surface strata to rigid deeper strata may lead to uneven settling if not adequately managed. Third, prolonged consolidation. Cohesive soils are anticipated to have time-dependent settlement, which must be accounted for in serviceability design. Fourth, construction oversight. Meticulous excavation and dewatering may be necessary to avert instability during foundation building. Notwithstanding these factors, the general geotechnical conditions are feasible for a low-rise edifice, such as a two-story residential building, provided that appropriate design and construction methodologies are employed. In conclusion, although the site contains weak compressible soils at shallow depth, the existence of competent hard clay layers at greater depth provide adequate support for the planned shallow bed footing foundation. The design is deemed satisfactory according to bearing capacity and settlement analysis. Nevertheless, soil enhancement actions may be necessary to improve a long-term performance and reduce settlement hazard.
Now, turning to our conclusion, I am pleased to report that our main project goal has been fully achieved. We have successfully evaluated the challenging subsurface soil condition at Pulau Indah, Selangor and engineered a safe, highly cost-effective shallow bed footing system for the proposed two-story residential bungalow. Geotechnically, the soil profile consists entirely of cohesive clay, silt, and clay. Although the upper 7.48 meters represent a weak, highly compressible zone, the soil strength and carrying capacity steadily improve with depth, which is clearly demonstrated by our rising standard penetration tests and values. To simplify our construction workflow, we group the columns by load range. We then apply the Zagi bearings capacity equation to verify that the allowable soil resistance comfortable exceed our maximum structural column force. Finally, our settlement analysis confirmed that predicted ground movement fall safely between 10 and 31 millimeters. This is well within acceptable engineering serviceability limits, guaranteeing long-term structural integrity and preventing any threat of differential distress.